In the vacuum of space, where sound cannot travel, there is one place that is quieter than anywhere else in the solar system. One place where the chaos of Earth can't intrude. That place is the far side of the moon, forever turned away from us, forever shielded from the electromagnetic noise we emit into the cosmos. And in that profound stillness, NASA has a vision: to construct a giant robotic ear, not to hear our own echoes, but to listen for something much older. This is the Lunar Crater Radio Telescope, or LCRT, a bold new mission to listen to the universe not as it is today, but as it was before the first stars were born. Why the far side of the moon? Because it's the only place within reach that offers true radio silence. On Earth, we are surrounded by noise, TV signals, radar, satellites, smartphones, and Wi-Fi, all saturating the low-frequency spectrum. Even the best ground-based observatories are compromised by interference. But the moon's far side is naturally shielded. Its solid body blocks all terrestrial signals. No artificial transmissions, no atmospheric distortion, no ionospheric bouncing of long waves. It is the perfect place to capture frequencies we've never truly heard. It is not just the remoteness that matters, but the purity of environment. Lunar dust never drifts in winds. There is no magnetic field to disrupt instruments, no tectonic activity, nothing to interfere. That level of stability gives the LCRT a clarity unmatched by any Earth-based system. These aren't just any signals. The LCRT is designed to detect radio waves longer than 10 meters, with frequencies below 30 megahertz, signals that are blocked completely by Earth's atmosphere. These are the waves that hold the key to one of the greatest mysteries in science, the cosmic dark ages. After the Big Bang, the universe entered a long period of darkness. At that time, it was filled with neutral hydrogen gas, cooling and expanding. There were no stars, no galaxies, no light. But even in that darkness, hydrogen atoms emitted a specific signal, the 21-centimeter line. A faint whisper from the early cosmos. Over billions of years, those signals have stretched and redshifted across the expanding universe. And now they're finally reaching us. The LCRT's mission is to catch these ancient whispers, to map how the first structures in the universe began to form, to observe when and how stars flickered into existence, to see how matter clumped into galaxies, and how the earliest forces shaped everything that came after. These observations could answer questions that have lingered for generations. How did matter transition from smoothness to clumpiness? What patterns were etched into the fabric of the cosmos before the first photons escaped? The LCRT has the potential to reveal the very first fingerprints of cosmic structure. To accomplish this, NASA will turn a crater, likely over 1 mile wide, into a massive radio dish. No rockets or landers will drill or blast. Instead, NASA's Jet Propulsion Laboratory has developed dual-axle rovers, robotic climbers that can descend crater walls, anchor themselves, and deploy a 1-kilometer-wide mesh of metal wires across the crater's span. These rovers represent not just mechanical ingenuity, but a bold step toward full autonomy in extraterrestrial construction. In an environment where delays can be deadly and human presence is limited, machines must not only build, but troubleshoot, adapt and refine their work with little to no human input. This structure will form the reflector for the telescope, similar in principle to Arecibo or FAST, but with no moving parts, no atmosphere, and no human crews. And once constructed, it could become the most sensitive ultra-long wavelength radio telescope ever created. The hydrogen signals it seeks are unimaginably faint, but in the moon's silence, the LCRT will be able to tune into the 21-centimeter line, redshifted into the low-frequency spectrum. This signal encodes a hidden map of the early universe, revealing its temperature, density, and structure long before visible light existed. The precision of such an instrument lies not only in its hardware, but in its algorithmic ears. Advanced signal processing, noise reduction techniques, and predictive models will pass meaningful data from cosmic background fuzz. It's not just about hearing the signal, it's about knowing what to listen for. This would be the first time humans have directly observed the cosmic dark ages. It's a moment we've only theorized. Now with the LCRT, we may hear it clear and direct across billions of years. The team behind this mission includes researchers Saptarshi Bandyopadhyay, Patrick McGarry, and Ashish Goel, all from NASA's Jet Propulsion Laboratory. Their vision is not only to open a new window on the cosmos, but to redefine how we explore the solar system, with robots building science platforms before astronauts ever arrive. But this mission isn't just about looking back. It's also about looking ahead. Our skies are changing. With satellite constellations multiplying rapidly, Earth is growing brighter and louder in radio wavelengths. Ground-based astronomy faces new challenges with each passing year. The more we connect Earth, the harder it becomes to listen to the universe beyond it. The Moon's far side offers a future, a place where astronomy can still be practiced in silence, where our thirst for knowledge doesn't compete with our technology, a refuge for pure science. And beyond the Moon, the LCRT could pave the way for telescopes on Mars, on asteroids, even free-floating arrays in deep space, all assembled robotically, all designed to listen to the past in new and powerful ways. These off-world observatories might one day be tuned not just to cosmic birth cries, but to biosignatures from exoplanets, pulsar interactions, and as-yet undiscovered astrophysical phenomena. The LCRT will also be a technological triumph. It will test our ability to design autonomous systems that build themselves in harsh, remote environments. It will explore new forms of artificial intelligence, adaptive routing, precision deployment, and autonomous decision-making under lunar conditions. As we venture deeper into the solar system, these innovations will be essential. Rovers capable of self-assembling instruments on moons like Europa or Titan. Satellites that can refashion themselves mid-mission. The lessons from LCRT will ripple far beyond its first signal. It is a proving ground for the next era of robotic science, and in the quiet between the stars it will be listening, not for us, but for the voice of the universe itself. What might it hear? The formation of the first black holes, the ripple of quantum fluctuations from the Big Bang, clues to dark matter, or answers to questions we haven't yet thought to ask. This is more than a scientific instrument. It is a monument to curiosity, a structure dedicated to silence, and a machine built to recover the very first story ever told. Out there, in the radio silence of the Moon's hidden hemisphere, we may finally hear the moment when everything began. Subscribe to follow this mission and to explore more breakthroughs shaping the future of science. Because sometimes the quietest places tell the loudest stories.